this is kind of the agenda that we have planned for today. First, I'll go over a little refresher of how often, in case you're new here or just kind of forgot what happened in the last 8 to 9 months. And then we're going to go over some of the preliminary results from the symposium. So Azza will be presenting her question and the results that came from it. And then I will present George's question and the results. And then Elise will go over how often and the connection to clinicaltrials.gov data. And then George will talk a little bit about the next steps for how often. Okay, next slide. So over the last couple years, Odyssey has done a lot of important work related to incidence rates. And we talked a bit about these in previous community calls, like last week, for example. But Odyssey has used large-scale incidence rate studies to provide information to the EMA and FDA as it relates to the COVID vaccine. Next slide. And we also looked at different methodological issues as it relates to how we compute incidence rates. And this paper that's in the middle here, we found that they're sensitive to a variety of different things, such as age, gender, database, and index year. Okay, next slide. So how often is our effort to characterize incidence of outcomes following drug exposure in a really large scale way? So last year, it did start sometime before last year, but the events of last year was that we had community calls in June and August to detail different aspects of this effort. Mostly before the symposium, we put out a call in the Odyssey forums for different research questions, as well as helped developing phenotypes, draft a protocol, as well as help build the analysis package. And then at the actual symposium itself in October in 2023, we had all of our data partners come together and execute the How Often analysis package. And at the symposium, we also had lots of really good discussions about the use of incidence rates and the reliability of incidence rates and how we might disseminate these results. Next slide. Stole this flow chart from Patrick because I really liked it, but everything in the blue is something that we've kind of accomplished before or during the symposium. And so the goal of this meeting today is kind of the orange part, and we're going to talk about some of the results. Okay, next slide. So coming out from the symposium, we had 6 different studies. So 6 different, I guess, question leads. And then each of these studies had multiple different research questions. So I totaled to more than 20 different research questions. And the kind of original questions and what they asked can all be found in the Odyssey forum. And then the protocol itself and then the analysis package can, of course, be found on the Odyssey GitHub. And as part of How Often, we use 265 different phenotypes. And many of these were actually brand new ones that were developed by our community as part of the How Often effort. And they're all in the phenotype library now. When we executed the study, we had 16 different databases represented. And this included both EHR and claims databases, as well as databases that are international, so from other countries outside of the US. And all of this resulted in 54 million incidence rates. And there's that many because we also stratified by age, gender, index year, and database. And then all of this you can see for yourself at this link, results.odyssey.org. Next slide. And if you go on the website, this is kind of what you see. This is an R Shiny app, and each of the question askers have their own like little How Often link. And yeah, that's it. Next. Oh yeah, so this is the result that we'll be going through today. And I think I'll just hand it over to Azza for now.
Okay, everyone. So we heard from Sydney how often work. What I'm gonna show you in the next 10 minutes is how we use the results that were generated from How Often to look at trends in hospitalization among patients with cardiovascular, immunological, and neurological illness. Those are all findings in How Often that you find on the links that Sydney showed you, and funny enough, with my name on the app. Okay, So a quick background, we all know that cardiovascular diseases are actually the main cause of hospitalization in the US and worldwide. Additionally, immunological and neurological disorders are on the rise, and they all together represent a most significant disease burden both in the US and worldwide. These conditions, the thing about these conditions is that they are mainly chronic, which means that they require continuous medical care and often leads to frequent hospitalization, which also associated, of course, with high healthcare costs. But how frequent are these hospitalizations is what we wanted to use our network to answer. So we really wanted to estimate the incidence rate of hospitalization across 14 conditions, stratified by age and gender, which HowOften protocol nicely allow us to do. We also wanted to look at the change of these rates over the past decades. So the method, which is very nicely presented in the protocol of HowOften, it's really represented in this. Let me take this down. We present here nicely a retrospective observational cohort design. For this particular preliminary analysis that I'm going to show you, we're leveraging data from 5 US administrative claims and 1 electronic health records. HowOften had more data partners, but the results I'm going to show you today is mainly from those 6 data sources. And here is the design in a schematic. What we did is a retrospective cohort where we index people on the day they've been classified as having any of these conditions. So we're looking at 14 different target populations. For cardiovascular disease, we looked at stroke, heart failure, myocardial infarction, and atrial fibrillation. For immunological disorders, we looked at psoriatic arthritis, plaque psoriasis, systemic lupus erythematosus, or SLE, ulcerative colitis, rheumatoid arthritis, and Crohn's. For neurological disorders, we looked at major depression disorder, or MDD, epilepsy, multiple sclerosis, and Alzheimer. So in each of these targets, the index date is the time that they were diagnosed. We required that everybody, and that's true for all HowOften, we require that everybody has at least 365 days of prior observation time in the data sources. And then we followed people for their time at risk, which in this case, we looked at 1 year post-diagnosis. So we looked at hospitalization, defined that as any inpatient visit that occurred 1 day post-diagnosis of any of these conditions, up to 365 days. So that was our time at risk. In this particular analysis, we also limited our results into the adult population. So we're looking at patients that have any of these diseases that are 30 years to 79 years of age. And I'm going to go straight to the results. First, and I'm going to show you this heat map or table that Patrick absolutely hates, but I wanted to really answer the simple question of how often hospitalization occur 1 year after diagnosis of any of these 14 definite conditions. So I really want to know how often, because we know there are multiple estimates in the literature, but what we have found, and you see here a heat map showing red colors toward a higher proportion, that's the simple proportion of hospitalization, and more toward green and yellow to a lower numbers. So as expected, the cardiovascular condition here show up on the top with high proportion of that is considerable. You see somewhere for heart failure, for example, somewhere between 43 to 60% of patients who were diagnosed with heart failure went into the hospital in that year that followed. And that is some ranging a little bit across the different 5 data sources that we use, but pretty high across the board. In contrast, for example, these dermatological immunological conditions, just as psoriatic arthritis or plaque psoriasis, have relatively a lower rate, but still range somewhere between 7.1 up to 31% in Medicaid, for example, for psoriatic arthritis. So considerable rates. I don't know what was your priority, but for me, it was like kind of an insight to see how much of hospitalization we see in these data sources. You also see here some pattern by data sources. So keep in mind, those are unadjusted rate, but you can see that some data sources like Medicare tend to show high rates across the board, while Informatics, for example, show a lower rate across the board. But again, those are not adjusted for age and sex. Those are just absolute proportions, but really answer the question of how often. So if we go to the more maybe valid estimates and look at incidence rate, I'm going to zoom into this a little bit more, and look at incidence rate on the y-axis, stratified by age. So every box here is a age 10 years of decile of age, starting 30 to 39, ending 70 to 79. In this case, for example, looking at myocardial infarction. A gender is presented with female being on the left side, and male being on the right side. Each data source is a different color, and the red color you see here highlighted is the meta-analytic estimate. We computed that number using a random effect model. So what you see here is we clearly see a pattern with age where generally the risk of hospitalization tend to increase with age, maybe not too much for heart failure, but when you look at cardiovascular, generally they're increasing with age. We see an interesting pattern with gender, where, for example, in myocardial infarction, you see higher hospitalization among female when compared to male. That's the opposite case of heart failure, where you see higher hospitalization for male compared to female, particularly in those younger age groups. If we look at the immunological conditions, another interesting trend, you clearly see the effect of age again, with higher trend with increasing age. It is interesting when you look at that 30 to 39 age group of female, across those immunological diseases, you see higher rate among female compared to male, which doesn't really stay doesn't continue when you go higher. Once you go into a higher age group, you see that males seems to have a higher rate compared to females, and that's true in all conditions of immunological condition. When you look at similar story, when you look at neurological disorder, MDD definitely caught my attention with a high differences comparing male to female, showing male with a higher rate of hospitalization when compared to female, and a very clear effect of age. So those are the age, gender kind of differences. The second question we wanted to answer is what is the change over time? And that is my favorite part of this presentation. So you see here the trends every year for the last decade, from 2012 to 2020, across the 14 different conditions. Each data source is presented by a color. The continuous line is the actual observed trend. The dashed line is a smoothing using a Poisson model. And the red line, again, is the meta-analytics. So generally, without going into the details, you can generally say that the trends over time, and the y-axis is using the trend of each data source. So it's not the same. It depends on the scale of each of the variation you see for the data sources for each condition. So you see that generally, it looks pretty much a stable line. So doesn't look like hospitalization rate changed too much over the last decades. You see a little dip here, which could be that's 2020. With the pandemic affecting hospitalization. And you might see a little uptake in 2022, but that could be just the instability of that last year of data that we use. But other than that, it's pretty much stable. What I found methodologically very interesting is that even though the meta-analytic trend is pretty stable, you see some fluctuation, or you can call it secular trend, that each data source kind of exhibit. If you zoom in a little bit and you take one line, one color, for example, if you take that green color, which is representing OptimHR here, you see it here in myocardial infarction. It's not all that different than the trend you see for heart failure. Very similar in epilepsy, similar to hemorrhagic stroke. So you see it across, there's some trend that is specific to OptimHR that is similar regardless of the condition you're looking at. Similar with, if you take Informatics, for example, that yellow line, it's somehow similar regardless of the condition, showing that data sources can exhibit a particular trend or a pattern that is specific to the data source that cannot be generalized once you take all the data sources together. So my conclusion is that, or our conclusion is that there's considerable hospitalization risk post diagnosis in most of these conditions, particularly the cardiovascular, Crohn's, and others. You would definitely see variation by age, gender, and data source, which we always kind of conclude whenever we look at incidence rate. Incidence rate, look when you look at hospitalization, which of course imposing a burden in healthcare system, regardless of the interventions we now have for these conditions. The methodologically speaking, those findings really underscores the value of using a network of data when assessing the long-term trend of any phenomena in health outcomes over time. This is because individual data sources may exhibit a secular pattern or trend that might be or might represent just a random noise or random noise related to the data source itself, that if you only look at it and don't look at other data sources, going to potentially distort the truth of the phenomena you're trying to understand over time. And that I would conclude. Thank you.
All right. So I'm going to be presenting on George's question, which I feel like can be very boiled down to the simple question of, does indication matter when we are calculating incidence rates? But I'll talk a little bit more about that. Okay. So as I mentioned earlier, Odyssey has done lots of prior work on incidence rates, and we also know that incidence estimates are sensitive to a range of factors like age, sex, calendar time, and database. And we also know that some drugs can be indicated for multiple diseases. So for example, SGLT2 inhibitors can be used for both type 2 diabetes as well as heart failure to reduce risk for hospitalization. And so the question we're interested in is, does indication matter? So basically, given that it's possible a single drug class can be prescribed for multiple reasons, is it also possible that the incidence of the different health outcomes could differ by the indication? And if that's the case, what is the extent of the variation? So the big picture method is that we use real-world data to calculate the incidence rates of various health outcomes across 12 different drug classes, stratified by indication. And then we compare the incidence rates for outcome across those different indications. And then finally, we examined if the rate differences by indication, if there is one, persisted when we further stratified by age and sex. Okay, going into a little more detail about the methods, we conducted the analysis on 13 different databases. October 2023 is when the symposium was. And then for the study design, we had outcome cohorts that are based on the first occurrence of a drug exposure in a patient's longitudinal record. And we found these people through, I guess, RxNorm. And then again, we had 12 different drug classes, and each drug class was further nested by their different indications. For our outcome cohorts, we had 73 different outcomes that were developed by the Odyssey community, and these can all be found in the phenotype library. And I'll give examples of what the target and the outcome cohorts look like in the later slides. Our time at risk was 1 day to a year after the initial drug exposure, and we used an intention to treat study design. And then we stratified by age and gender. And then for each of these target outcome pairs, we calculate the incidence rate, which is defined as the ratio of the number of cases to the total time at risk for all patients in the target cohort. All right. So as promised, these are the 12 different drug classes that we looked at. 8 of them had 2 or more indications. And of the drug classes with 2 or more indications, 6 of them had exactly 2 indications. And then beta blockers had 3 indications, and TNF alpha inhibitors had 5 different indications. But anyways, this is just an example. Okay. We had 73 total outcomes, and they're all from phenotype library. They span different organ systems, and I just chose 3 here to show as examples, since it's a little hard to make 73 things look pretty on a slide. So obviously there are other outcomes here that are not included here, and this is not comprehensive, just a little sampling. For the analysis, we conducted a random effect meta-analysis of incidence rates across the 13 different databases. And then we compared the difference in indications with the fixed effects moderators model. And this was only done for drug classes with more than 1 indication because, yeah. For the outcomes where incidence rates were deemed to be significantly different by indication, we also found the standard deviation of the effect estimates across the indications to see which one differed the most, which outcomes matter the most when it comes to indications. And then all of this was done in R using the metaphor package. So based on the target, outcome, and time at risk, and also the stratifications that we defined, there's a total of 77 incidence rates that were calculated. And again, all of these are available publicly. 8 of the drug classes, as I said, had at least 2 indications, and they're all listed here. And the last column in this table shows how many of the outcome incidence rates differed significantly across indications. So for example, we had 73 outcomes for all of them, but for beta blockers, 61 of the 73 outcome had like a significantly different incidence rate across the indications. This honestly would be a lot of information to try to go through in 10 minutes. So we're going to zoom in on just one of the drug classes, and we'll zoom in on beta blockers. So this is the first 30 of the 73 different outcomes, and there's really no reason why I chose these 30 except for the fact that they're the first 30 in my graph. And I just have limited space on the slide, but I'll walk you through what you can see here. So on the x-axis, we have the different indications for beta blockers, which in this case are hypertension, left heart failure, and acute MI. And then on the y-axis, we plotted the log incidence rate. And each line represents a different database, and each panel is one outcome of interest. And if there was no differences between the indications, then we should expect to see more or less a flat line. And if there was a difference between indication, then we would see some kind of like slope between each indication. And because there's 3 different indications here, we would just see like a triangle situation. Okay. And in addition to differences by indication, we can also see there's some database variability. It's especially obvious in these events, for example, where there's just like a bigger spread between the different colored lines. Okay. So among the outcomes with significant differences between indications, we also found the standard deviations of those effect estimates. And the 3 outcomes with the highest standard deviations across the log incidence rates are hospitalization with heart failure, 4-point MACE, and then total cardiovascular disease events. And this just means that these are the outcomes where I guess the indication would matter the most, though this is a pretty like basic kind of measure. And the outcomes where there's the lowest standard deviations across the rates were gout, bone fracture, and cough. One thought on why indications might matter will be like, well, maybe we're just measuring different populations, and that could be true. So we tried to see if these differences by indications were preserved even when we stratified by age and sex. And so here we stratified by sex, and these are just 3 outcomes that I plotted. I chose these because they looked particularly bendy on the ones without stratifications. And again, on the x-axis here, these are the 3 different indications. And top row is female only, and then bottom row is male only, and then each column, I guess, is one single outcome. So you can see that the trends of the differences between each indication is pretty similar. So they're still bendy. So in this case, the differences in incidence rates across the different indications is like not necessarily because of gender. And we did the similar exercise for age. And here again, each column is a single outcome, and then each row is a different age group. And again, the trends of differences across indications are preserved even when we stratify across age, with the exception of maybe like the highest age group and also the lowest age group. The highest age group, that makes sense why we don't see as much of like a similarity in trends just because there's less data there. But yeah, it looks like the trends are pretty similar even when we stratify by age. Okay. So what are some of the key takeaways? We found that the meta-analyzed incidence rates were for beta blockers were sensitive to stratifications by indications, and that the trends of these incidence rates across indications are preserved even when we stratify by age and gender. And among the 8 drug classes that we included in our analysis, trimethoprim was the most sensitive to stratification by indication, and then GLP-1 the least sensitive. And as we move on to expanding this project to explore all exposures and all outcomes of interest, which George will talk about at the very end, it shows like this preliminary kind of analysis shows that it might be important to nest exposures within the different indications. And that is it for me.
Great. Thank you, Cindy. I believe our next speaker is going to be Elise.
Sure, let me share. So I'm going to shift gears a little bit to talk about some of the work we've been doing with clinical trials data, specifically standardizing the reported adverse events data for the purpose of large-scale incidence rate calculations. So much of what we know about potential adverse events currently comes from pre-marketing clinical trials, and data from these trials are entered manually by researchers and is available via this AACT clinical trials database. And one specific data element that's included is reported adverse events. And so in which researchers are asked to report any unfavorable or unintended signs, symptom, disease that are temporarily associated with the use of the intervention drug and without passing any sort of judgment about causality. So we originally looked at this data source as a potential way to evaluate the outputs of and compare the outputs of the HowOften work, where we're doing, as we've talked about, the large-scale incidence rate calculations. And so the issue is that these reported events, as well as many other data elements in the clinical trials database, are entered as unstructured text entries, which makes this type of analysis challenging. So our 3 initial objectives for this work is to first take the clinical trials data, which is, as I said, available in this relational database, and mapping the unstructured text entries to standardized concepts in the OMOP common data model, using RxNorm for the intervention drugs and SNOMED CT clinical conditions for the reported adverse events. And in this, we can also evaluate what proportion of these text entries can be successfully mapped to a standardized concept. Once we complete the mapping, our second objective is to then use them to perform large-scale calculation of incidences for each of the drug condition pairs. And so from the first step, we'll get the standardized concepts for drug ingredient and reported adverse events. And then we'll get the study ID, number of subjects affected, and number of subjects at risk directly from the clinical trials data. And so this would be enough to calculate the cumulative incidence proportion. But if we want incidence rate, there was actually also a time frame, like a follow-up time frame data element. Unfortunately, once again, also unstructured string text entry that we mapped to the closest estimate of a time at risk. And notably, this wasn't possible for all of them. But if we are able to estimate this, then we can estimate an incidence rate. So now we have for each study what the intervention drug was, what the reported adverse event or condition was, the number of subjects who had that condition, and the number that were at risk. And if we wanted to then pool these studies together to get the pooled incidence rates for each of the drug condition pairs across all their studies. And then our final aim is to then look at the variance of the calculated incidences. So in that for each drug outcome pair, we want to describe the variation in calculated incidence between studies. And how we decided to approach this is a little complicated due to the limitations of the data, but I'll get to that in just a bit. So for our first objective, what we did was extract a static copy of the clinical trials database up until June 2023. And so we had all the trials that were submitted prior to that, which is about 400,000. Looking only at trials that had one reported adverse event data, where the intervention type was a drug, the drug was a FDA approved drug, and none of the interventions had placebo or control in the name. Another issue we ran into was that the reported adverse event data was for what they called results groups, and the result groups names were not standardized in any way. So it could be anything from the actual intervention drugs, or it could be like just group A versus group B, or part 1 versus part 2. So to try and mitigate the issues from this, we excluded result groups that had the words control or placebo in it. And then also for our incidence calculations, we focused only on trials that there was only one intervention listed. And so the mapping was done using manual review and the Usagi tool, which is an Odyssey open source tool that helps start the process of mapping. But we did have 2 clinicians go through and manually check all the mappings and then adjust them as needed. Text entries could map to more than one concept for drugs. So if the intervention was listed as a combination drug or a chemo regimen, we would map to all the drugs that were listed in the drug ingredients listed there. And we found that the majority, over 80% of the text entries mapped to a standardized RX norm concept. And some of the reasons that we found for when they couldn't be successfully mapped were the text entry was a drug that was still very new. There wasn't an RX norm associated with this, and it was just like the pharmaceutical number. Others reasons were the intervention was listed as an entire class of drugs like beta blockers, and so we couldn't tell exactly what drugs were used easily from the data. And then another reason is if the text entry just had insufficient details. So sometimes it would be like standard therapy, in which case it just isn't clear also what they used. When mapping the reported adverse events to clinical conditions, similar to the drugs, we also found that the majority, over 80% of text entries, were able to be mapped to a standardized condition concept. And then some of the reasons for why they weren't able to be mapped were events that were not conditions. So like procedures, the patient getting a surgery, sometimes it's reported as an adverse event, lab abnormalities, or some stranger ones like mugging or domestic violence. And then also like drugs, there were some entries that were just overly vague, like complaints or side effects. And so the final data schema with the mappings added in, so the 2 tables in the middle are directly from the clinical trials data, and then we used the mapping and the codes to map to a standardized concept. We also did map the timeframes to a time at risk, as I said, and we only did this for the ones where the trials had only one intervention, because this is for the purpose of incidence rate calculation. So there was like about 2,000 more string entries. But moving forward, when I'm speaking about results, I'm going to focus just on the cumulative incidence proportion, just because it's a little bit easier to calculate. But we do it also for incidence rates. But using the data schema from the last slide, what we're able to do is get a table that looks something like this, where you have the drug, the condition. This is more like trial ID, not number of trials. The number of subjects reported to have that condition, and out of the number that were at risk. And from this table, you can get a calculated incidence and variance for each of the studies. And next one, if we want to pull these together, these studies for a drug condition pair. If a drug condition pair only had one study that reported on its incidence, then that's all you can really report. We didn't do like a confidence interval, and obviously we can't do a prediction interval here. But if there were more than one study that studied both the drug and condition, then we can use a random effects meta-analysis to pull the incidences and generate these prediction intervals. Additionally, we did a logit transformation and back transformation due to such large variations in scale for the incidence and variances, often due to the varying sample sizes. And so this is an example of what the final data looks like. And then, but moving on to our last objective, so unlike incidences and the prediction interval, for measures of variance and heterogeneity, you can't really easily back transform into a linear scale. But if we were thinking about that, we were just trying to compare the degree of variance and heterogeneity, then we figured we could get away with just kind of staying on the logit scale and comparing the results. And so moving forward, this is all going to be like the meta-analysis of the logit of the calculated incidences of variances. But we spent a long time also thinking about what measure would be most relevant for our questions. And our questions are, one, how much variation is there between the calculated incidences of different studies studying the same drug and condition? And two, are there conditions that have more variability or heterogeneity, perhaps due to variable capture in the data, different phenotypes or presentation of patients? And then similarly, maybe not as relevant, but for completeness sake, are there drugs whose adverse events are reported at similar or less similar rates? And so the measures that we looked at that were outputs of the meta-analysis were tau squared, which is a measure of inter-study heterogeneity, VT, which is the typical sampling variance, and total variance, which is the sum of both tau squared and VT. And this is what is used to calculate the prediction interval. Some of the issues with deciding which measure to use is that many of the drug condition pairs only had like 2 studies, which makes the inter-study heterogeneity value of tau squared have a tendency to underestimate and truncate and many would truncate at 0. Additionally, some of the studies had really low sample sizes, and we don't necessarily want to use a measure that is strongly impacted by sample size. That would lead us to say, there's a lot of variance in results, but that was really just due to the fact that the studies had either very low sample sizes or had very different sample sizes. So what we decided is that if tau squared, or the interstudy heterogeneity, is high, then we feel confident saying that there is high heterogeneity because we know it tends to underestimate, if anything. But if total variance, in that both tau squared and the sampling variance are low, then we'll consider there to be a high agreement between studies. It'll help to look at some examples, but basically, if we aggregated by condition, and so in the example here, you'll see that heartburn had 7 drugs that had heartburn as a reported adverse event, and their tau square, sampling variance, and total variance are all listed here. And if you take the median, you'll get a median tau squared of 0 for heartburn and a median total variance of 0.19. But for a condition, and so you would say like there's probably pretty good agreement for heartburn. But for a condition like hemarthrosis, we found that we actually had high heterogeneity in that the median tau squared was 2.41. And it's helpful to work backwards to see why this might be the case. And so for hemarthrosis, there were only 2 drugs that reported it as an adverse event. It was vitamin D3 and empagliflozin, and each of the pairs had 2 trials. And so the high heterogeneity makes sense when you look at the trials because each of the pairs 2 studies had very different incidences, like 2 out of 22,000 versus 2 out of 300, and 1 out of 150 versus 1 out of 3,000. And there are any number of reasons why there is such a difference between studies, such as different eligibility criteria, administration route, dosage, indication, and we can't really easily glean the reason from this data. For drugs, an example of a drug that had high agreement was tramadol, and you see that both tau squared and the total variance are low, versus dronabinol, which had a high median tau squared. And if you remember from a previous slide, I had dronabinol and nausea as an example, and it had 2 trials that had an incidence of 0.06 and 0.5, so significantly different, and also pretty low sample sizes. And so there's quite a lot of challenges and limitations to this approach, mainly due to the way that the data is entered. So because there was so much kind of like unstandardized, difficult to map data, there was a lower proportion of included studies. And then also the issue I mentioned about the results group made it so that we had to exclude a lot of studies that had more than 1 indication drug listed. There was also a low proportion of studies per pair, like I said, that made the evaluation of heterogeneity and variance challenging. And then this issue I actually just discovered when I was going through an example, and I'll probably speak with the rest of the people working with us on this. But if we look back at the heartburn example, I noticed that 5 of them had the exact same tau squared total variance. And that's actually probably because there was 2 trials that were evaluating R-CHOP, which is a chemotherapy drug regimen that includes these 5 drugs. So that kind of artificially brings down the median if we want to count this as 5 different calculations or just 1 because it was 1 study. And so just some kind of broader takeaways. We found that the majority of the text entry strings entered into the clinical trials data could be mapped successfully to a standardized concept. And doing so would support large-scale calculation, and the way that the data is currently organized makes it challenging to do such analyses. But I think clinical trials was like putting an ask on their, like, revamp the way that their data is collected and structured. And I think kind of being more deliberate about what people can enter for these different data elements would help. And that we are able to evaluate the heterogeneity and variance and results for these incidences, although because, as I mentioned, because of the issues with the data structures, we're not able to easily glean why there is heterogeneity or not. And so currently what we're doing is obviously writing up these first 3 steps. But as I said, the original goal of this work was to be used as a comparison reference for the results of the HowOften, both in comparing what the actual found incidences and prediction intervals are, but also the variance and heterogeneity to say, the difference between results between databases is comparable or not comparable to the differences we found between studies. So I'll stop it there. Yeah.
Great, thank you, Elise. To hear a little bit about next steps, I'll turn it to George.
Hi, I'll hold off on slides since we only have a couple of minutes left. But first, let me say thank you to Cindy and Azza and Elise for presenting on this. And it's fun to see some outcomes from, we did an activity in a symposium almost a year ago, and just showing that, we did follow up. So when you participate in activities at an Odyssey symposium, they're not forgotten. We follow up and try to come through and deliver real evidence or, useful methods from them. So that's the first thing. We can learn useful things as Azza presented, or learn about it as Cindy and Elise presented Elise's results. What we're trying to do there is if we have incidence rates from the clinical trials, let's first of all, I understand the populations may be different, but the information sitting there on the internet, let's pull it down. Let's use what we can and also learn not just about the actual rates, but the differences among the rates. So when people complain, are our rates good? Well, first, what is the expected difference between rates when you do it in a prospective, very careful, very expensive way, as you might in a clinical trial? We would like to pull forward with the next step. And in fact, I presented this in 2017, if you remember the all-by-all HowOften study. So that's every drug in the world, every side effect in the world. There's about 40 million combinations, a little more. Depends on how you count them, of course. And we'd like to move forward with that. We don't have the package ready yet, so perhaps at a future Tuesday community call, we'll present a little more details on that. We have 40 million pairs. Then you have to decide, am I stratifying how many age groups, sex at birth, time at risk? And then are we going to stratify by education, not education, indication also? As we noted, indication does matter, but does it matter enough to add another billion queries or not, or do we do a first pass? So we will be coming back to you with a request to run the all-by-all study. We'll have the package ready. I think it'll be iterative, and even if we got it right the first time, we're still going to want to keep it up to date. We'd like to create a resource that just states, here's the incidence rates of everything. Now, so first of all, there's the incidence for each drug or treatment. There's also the incidence without drug or treatment. That is just the incidence rates of every condition we can think of by age, sex, and whatever else we stratify by. So we might as well have that online in data.odyssey.org. So if you're doing background rates on something, you can just look it up, and we think we'll have the best methods available. And we will then, as Elise mentioned, be comparing that to the trial rates that we've already gotten. So there are a couple of projects that need to be done, like we need the phenotypes. So one is to do the code. We can also pull down all the phenotypes in the library, but there may be something in the middle, maybe not as numerous, but not as simple as a single code in SNOMED, but not as detailed or proven as every phenotype in the library. So what's the intermediate ground between those two? So that's one thing we need to work on. We need to work on communication. If we put these things on the network, on the internet, we don't want people to be misled by it. We don't want them to look at a high heart attack rate in statins and stop their statin, because that statin is helping their heart attack rate, even though the incidence is higher than the general population. How do we explain causality to the general public if they look at our database? So there's a lot more to talk about. I'll stop here, but I hope you'll come back. We'll present at a future meeting with the package to move to the next. But this is one is saying that if you do join us and help us calculate rates, it won't be going into a garbage bin, that we actually follow up on these things, and that's what this meeting is about.